Okay. All right. So today we are going to be starting on a new module, magnetostatics. How's it going? We spent a lot of time on the last module. Module 4 was huge. There's over close to 100 slides, I think. So we're going to spend time on magnetostatics, which is going to be substantially shorter than module 4. This is going to be the second half of class today. The first half of class is going to be just open Q&A for the exam, and we can start with all the homework questions. So let's do that. I had a lot of good questions on the homeworks, including a few corrections where I made a mistake on the solution. So Brad, thank you for the email about the corrections. The corrected homework solutions have been posted on Blackboard. So if you haven't downloaded them yet, they're already corrected. So I thought what we could do is let's go over these homework problems, and if you have older homework problems or conceptual questions that you'd like to go over, let's do that in prep for the Wednesday's exam. So let's keep it open Q&A format, and as you ask questions, I will then go over those relevant sections in the notes and so on. Yes.
Number 5 on homework.
Okay, number 5. Okay. Yes. Okay. Number 5. Jeremy. Oh, what's the question you had on number 5?
What if I change the fact that, what if I put it above the materials made contact on the y=0 plane? How should the equation be?
If this was the y=0 plane?
Yes, because the z=0 plane, it says that there was the reasoning behind because the contact is at z=0 plane.
Correct.
The z coordinates for each j vector stays the same, and x and y are different.
Correct.
So I don't know what's the difference between if I have, like I say, y=0 plane.
A y=0 plane. Right.
The opposite. Yeah,
it's a good question. So Jeremy's question on number 5, and this would also apply to number 4 as well, right? These problems 4 and 5, notice that the interface between the two materials is the z=0 plane. So the question is, what happens if I give you some other arbitrary plane? So I could give, in fact, the example that we did in class was actually an arbitrary plane. Okay. So let's just touch on that a little bit, because I think that is an important concept. So if we're going to go to the section where we talk about boundary conditions, the fields at interfaces. Okay, so this is how you solve electrostatics fields at interfaces. You use these two key boundary conditions. The tangential components of the electric field are continuous, and the difference in the displacement fields, the difference in the magnitudes of the displacement fields, the normal components of those displacement fields, is equal to the charge density. Now, Jeremy's question was, what do we do when, if I give you an arbitrary plane? You know, an arbitrary plane would be more difficult than just giving you the z=0 plane. You have to find the normal vector of that plane first. So you start off with, let me see, did we do an example of that? We did. I think it was in the I think it was in OneNote. So give me just a sec. Let me see if I can find it.
Professor, do you usually
Yes.
post the solution of the slides?
Do I usually what?
Post the solutions of the examples. You see the examples on the slides? Lecture? No?
Oh, well, I don't put the solutions in the slides themselves because I want you all to follow along in class. So,
I'm saying after we're done lecturing, if you want to review the slides.
Since we have like an exam Wednesday, can you like post it? There is some examples that.
there are some examples, and I just have the answers. I don't have the work. The work that I show is actually here in OneNote. You know, yeah, I could. I mean, I have the lecture recordings where we go over them. So that's what I would want you guys to do. Just go over those sections of the lecture, so you can go through them step by step. So it looks like we have. Well, I think this was the problem that we had actually done on the board because my OneNote wasn't working that day, if I remember correctly. So what you have to do, if you have to first find the normal component of the surface that we're talking about, right? So in the example problem I gave in class, I said that you have an electric field E equals 1, 2, 4 that's incident on a surface with a surface normal 1, 1, 1. You guys remember doing this problem?
Yeah.
I think in the solution you posted, there's something wrong with the calculation. I think so. There's no. I was doing that.
You mean the solution of the homework?
Yes.
Okay, let's take a look at it. Which?
I think if you go down, I think in this question, yes.
Okay.
Yeah.
So let's go to question 5. All right.
No, 4.
Question 4.
Yeah.
Okay.
So you see
Which part here? The first part?
the second. Scroll down a little bit.
Okay.
Okay. See there. You multiplied all that. The 3 is supposed to be a vector. It's supposed to be 0, 0, 3. So you multiply the whole thing with this.
Well, which part is 0, 0, 3?
E1n.
E1n. This part here?
Is it supposed to be the magnitude of it, or?
Yeah.
The magnitude of it.
Oh, that is magnitude. Okay.
It is the magnitude of it.
Okay.
Yeah, this formula here, the two boundary conditions, the tangential components are equal to each other, so these are vectors. And the normal component is, these are the magnitudes of the normal components. Yeah, there's a few students who ask those questions, so I appreciate that clarification.
Oh, that's another question I asked too.
Yeah.
How do you know that it was 0 to 0, 0, 1 vector for this question? So it was 0, 0.
That's the zero. That's the z-plane. That's how you describe the z-plane.
Oh yeah. That gets back at your original question. So yeah, glad we came to that. So in this case, in this question, I mentioned to you in class that the interface between these two planes is a z equals 0 plane.
Okay.
So if you imagine the z equals 0 plane, the vector that's perpendicular to it is the vector 0, 0, 1.
So based on this picture, how would you know that just looking at it?
It's not clear just by looking at this picture.
Okay.
I think Justine or someone had asked in class, what plane is this that we're looking at? I mentioned in class that it's the z equals 0 plane.
Oh, okay.
And if it was a test, I will definitely make it clear.
So it is top-down perspective, is what you're saying.
Yeah, the Z is pointed upwards here.
Okay.
Z is pointed up, and then the left and right are the X plane shown there.
Okay.
Justine, yes.
I didn't see the solution for the angle of this
Oh, yeah, I see.
in here. I don't know if it's been updated since.
Oh, maybe it's possible I forgot to put that.
Yeah, it's not there.
Okay. All right. So let's do that.
Yeah, angle of incidence should just be.
Question, this is 5? No. It's 5. So it's 4.
Oh man, my pen is not working today. All right, can everyone give me a few minutes while I reset this? I don't know why my computer gives me a hard time with this. All right, I'm gonna stop this recording here, and we will